all the resonant, quasi-resonant type, and especially LLC converter. I don't have a time to talk about it, but if you have questions, I'm glad to answer. So because of that, I think I go back to my basics. And the basics are, in 1970, Caltech started as a second university PhD program or research program at university in power electronics. First university was Duke University with Professor Wilson and his colleague. And so I republished 3 of these volume books will be available now through Amazon and through their subsidiary CreateSpace. Fourth volume, I added my PhD thesis for 2 reasons. One is that half of my PhD thesis of 300 pages is a state space averaging. And I'm sorry to report that after 40 years, since actually 1976, 75, when I came up with the state space averaging, I gave a talk at APEC on it, and I'm sorry to report that even my best PhD students didn't get it. Okay, so hopefully now with this republication and with the 4 patents I had on a CHU converter, which deals with basically integrated magnetics and coupling inductor methods, which are still applicable to my new technology, that this will be a good start to get into, to understand my new system technology that I'm developing right now. So here is where I feel that power electronics was stunted in its growth for last 40 to 50 years. Okay, I came on board 40 years ago. When I came, it was, as I showed here, my first papers that I was publishing, and I was giving 5-day course, which was called Topologies, Magnetics, and Control. Okay? I consider this field difficult because it requires expertise of all these 3 areas: topologies, magnetics, and control. Now, inside of magnetics, as you'll see here in this triangle that Bill Newell put together, electronics is one part which talks about circuits, which I renamed the topologies. Another part talks about devices. I consider devices not really separate from topologies. Let me explain what I mean by that. And unfortunately, nowadays, so-called power management companies, they'll talk all about devices, and they don't care about topologies. It's all given. You know, you're using it for 50 years, we'll use another 50 years, right? Well, the problem is that topologies are important because how you connect switches, inductors, and by the way, that's all conventional topologies have switches and inductors and transformers. They don't have a capacitor inside a converter. My CHU converter, when I introduced in 1976 at a conference, same conference, PESC, where it was CPIC introduced by Bell Lab, the only 2 converters with a capacitor inside the converter. Now that what is important is then with some of my students, I develop a synthesis method, how to come up with a new converters which will show connection of ideal switches. Ideal switches, just, you know, on and off switch conducts a current in both the 4-quadrant switch, conducts a current in which way and blocks the voltage. What is then, how did we come to the devices and put devices in it? Well, once you come up with a new topology, then you have to determine for each of, say, 4 switches, what the switch is. If it conducts the current in one direction and blocks the voltage positive, negative, it's a transistor. But if it conducts the current in opposite direction and blocks the voltage, same blocking voltage, opposite of transistor, it's a diode. Well, if it requires that during operation of duty cycle the current changes, then you have to have a current bidirectional switch. If a voltage changes, you have to have voltage bidirectional switch. All I'm saying is type of a switch is dictated by your original topology. It has nothing to do whether it's a MOSFET or gallium nitride or IGBT, etc. And now, I think what's happening, the whole power electronics field was turned upside down in the sense that all 3 sides of this triangle, I call them, one side is IGBTs for high power, the other side is a MOSFET or silicon carbide MOSFET, and the third side is gallium nitride. But that's not going to solve our problem. They're going to still be operating lousy and having a lousy conditions for design because that depends on topology. Magnetics also depends on topology. What I go show you today, that the magnetics can be 10 times smaller, so you don't need to go to 1 megahertz. Okay, let's move on, otherwise I could spend a half day just talking about it. Here it is. What's the problem and why I say it's a really bad news that Buck converter, actually, what I now kind of a joke and said, there is a Mr. Buck who patented it, but there is nobody who patented it, right? And if I think it always existed, Buck, boost, and the flyback. Why did they exist? Because it was so simple-minded. Buck is switch, you switch on and off. On the front end, you generate a square wave voltage, and you have a low-pass filter. Bad news is we have the inductor. And that inductor is really not inductor. It's inductor, not AC inductor, it's inductor with a DC bias. So what happens? You conduct a DC current through it, it's going to saturate. Now, let me give you a story, which was my warning some 20 plus years ago. I don't even know, we can look at the record. When the first Lisa computer was being made by Apple, I had a connection with a Solectron, which was manufactured in Silicon Valley at the time, and it said, hey, we'll use a true converter, you replace flyback 150 watt with your converter. In my converter, I still had an output inductor. It was 5 volt, 30 amps, so we are talking about 150 ampere turns. Now, for 150 ampere turns, you are having yes, let me just show here. For 150 ampere turns, you're talking at 20 kilohertz, you needed some decent inductance. But what happened? At 150 ampere turns, at 20 kilohertz switching, you have about 1/4 millimeter of the gap. I kind of exaggerated on this picture that you see here that on the first photo, it shows how by increasing the air gap, the slope of the inductance, slope of the flux versus ampere turns goes down, and that is the inductance of the core. And long story short, to make long story short, when they made prototypes, 200 prototypes, they forgot to specify the gap, this 1/4 millimeter gap. You know what happened? Well, funny enough, converter worked. The only thing we knew that it wasn't there are some problems with it because ripple on the output, instead of being for 5 volts specified 50 millivolts, the ripple was 125 millivolts. Why? Well, we looked further into it and found out, oh, these guys ordered the ungapped core. So there was no gap. So the core was saturating, and inductance you got with that core that we selected, pot core, the inductance we got, what is happening? Did I press something? Okay. The inductance we got was only with the whole core inserted in it, but because gap dominates, the inductance was 2.5 times smaller than without the core than with the core. So core only increased the inductance by 2.5 times because that slope that you see here was so low. And my point is, everybody talks nowadays, oh, we'll go to 2 megahertz, and it's not good enough. We go to 10 megahertz, and then finally we can make that inductor which doesn't have any core in it. I'm telling you, hey, you are 30 years late, right? Because at that point, when we're switching at 20 kilohertz, all I could do is take the whole core out, because it was just generating core losses, right? Because it was inside, and make it an air core inductor, and I make up for a 2.5 times loss inductance by increasing frequency from 20 kilohertz to 50 kilohertz. End of story, right? The problem is then that inductance is an energy storage inductance proportional to the current. So if you now want to go and make instead of 30 amp, 150 amp current and 5 volts, that's 750 watt, what happens? Now you have to increase the gap, even more, so then it's even worse. So what you do is you keep increasing switching frequency. You increase switching frequency to the point, like say 100 kilohertz, 5 times for 20 kilohertz, and now you're okay. You can use 5 times more current, so it's instead of 30 amps, 150 amps. Oh yeah, but that's not good enough because you say, yeah, I'm switching at 150 kilohertz, and look, still the core is this big, right? So what do? Well, let's go from 150 kilohertz to 500 kilohertz. Now I can make a core cross-section smaller, okay? And then now the gallium nitride is here. Let's do 1 megahertz or 2 megahertz. You know what we forgot? The only thing you can do with it is buck converter non-isolated, and that's bad to start with, okay? And even that doesn't allow you to make even 12 volt to 1 converter anything decent, because you have so much other problems which I'll describe in a minute. So basically, the problem is if you want to have isolated converter, so everybody says, okay, we'll make isolated converter. The only problem is it's the same prototype. Transformer has to operate in megahertz just the same as an inductor operating in 1 megahertz. And what happens with the transformer in 1 megahertz? Well, TDK and other companies say, well, don't worry, we'll make you special high-frequency material, all right? At 500 kilohertz, you're allowed to have 50 millitesla. At megahertz, you're allowed to have an AC flux swing, peak to peak, 20 millitesla or 10 millitesla unidirectional from 0 to peak. Well, but you know what happened? When you use that high-frequency material at 500 kilohertz, you go to 300 kilohertz, and it's a 7 or 8 times higher core losses. And they don't even specify it at 250 kilohertz because it's so ridiculously high, and it's not. But do you gain anything by 50 times reducing AC flux swing in a transformer from 500 millitesla one directional or minus to plus 500 millitesla 1 Tesla flux swing? You're reducing it to plus minus 10 millitesla. You're reducing it 50 times. And what you get in the size? Nothing. Just the core losses. Transformer has a skin losses. Transformer has proximity losses, eddy current losses, and so on. Who are you fooling? Okay, nobody. And the other point, if you go over 150 kilohertz, you have to meet EMI conducted noise, EMI radiated noise. If you have constant switching frequencies below 150 kilohertz, there's no regulation dealing with that. Okay, let's move on. So here I had a demonstration, a video, but because we don't have a time, I just put it in one slide which shows on a pod core, you can change the gap continuously, and you see how the BH loop of that inductor shears over and comes down to very little. So my point is this, concluding, if we are doing anything to do with the inductor, with the DC bias filtering or output, it is power limited. You are just fooling yourself by increasing the frequency and making the buck converter, you know, with the inductor 1 turn and whatever. You can't do anything else with it. And at a certain point, if it's of 5, 10 kilowatts and you need a charger 25 kilowatt for a car, forget about the full bridge. It has the same inductor limiting the power as the buck converter because it's a buck derived. Oh, worst of them all is actually forward, not worst. Forward is second worst, and then flyback, of course, is totally lousy because you store all the energy like in inductor of buck converter, except you have no help with the filtering because input current is pulsating, output current is pulsating. Okay, so we move on. Well, what's the solution? Here I compare the step-down buck, and you know what is the people now with gallium nitrides, what they're saying? You know, which I really get annoyed because those device people had no idea what we are talking about in terms of circuit design and topologies. They say, oh, great. Now I can operate, instead of 500 kilohertz MOSFET, I'm going to operate it at 2 megahertz, and guess what? I can go now and make a 40